Welcome to this walkthrough of LeetCode problem number 37, Sudoku Solver. In this video, we'll tackle the challenge of solving a 9x9 Sudoku board while adhering to its constraints. Stick around as we explore the problem, break it down step by step, and implement an efficient solution. Let's get started. In this problem, we're tasked with solving a 9x9 Sudoku puzzle. A valid Sudoku solution must follow three specific rules. First, each digit from 1 to 9 must appear exactly once in every row. Second, the same digits must also appear exactly once in every column. And third, within each of the 9 smaller 3x3 subboxes that make up the grid, the digits 1 to 9 must also appear exactly once. Empty cells in the puzzle are represented by the character dot, and our goal is to fill these cells to complete the puzzle. The input is given as a 2D list of characters, representing the board, and the function should modify this board directly in place to produce the solved configuration. It's important to note that the function does not need to return anything, as the board itself is updated directly. Let's look at an example to better understand the problem. Here's an input board where several cells are empty, represented by the dot character. For instance, the first row contains the numbers 5, 3, and 7, but the other cells are empty. Similarly, other rows have a mix of numbers in empty cells. The goal is to fill in all these empty cells while ensuring the solution adheres to the Sudoku rules. The output shows the solved board, where every row, column, and 3x3 subbox contains all the digits from 1 to 9 exactly once. Notice how the previously empty cells are now filled with numbers that preserve the constraints of the puzzle. Continuing with another example, we have a different input board with more empty cells. This board has fewer initial numbers filled in, making the puzzle more challenging. For instance, the first row contains only the number 2 and a 6, while most of the other cells are empty. Despite this, the output shows a valid solution where all rows, columns, and subboxes contain the digits 1 to 9 without any repetitions. This demonstrates the importance of carefully applying the backtracking algorithm to explore possible solutions and ensure the rules are met. In this output, we see the result of solving the second example. The filled board now satisfies all the Sudoku rules, with every row, column, and 3x3 subbox containing unique digits from 1 to 9. For instance, in the first row, the digits 5, 4, 9, 2, 7, 8, 1, 6, and 3 appear exactly once. Similarly, every other row and column in the output follows the same pattern, ensuring a correct solution. This highlights the algorithm's ability to handle even challenging boards with many empty cells, as long as at least one valid solution exists. Finally, it's crucial to note a few constraints and edge cases for this problem. The input board is guaranteed to be a valid 9x9 grid, containing only the digits 1 to 9 or the dot character. Additionally, the board will not have invalid configurations, and at least one solution is guaranteed to exist. The solution must modify the board in place without creating a new one. While the algorithm's time complexity is exponential in the worst case due to the backtracking approach, it is still effective for practical Sudoku puzzles. Edge cases to consider include boards that are already solved, boards with only one empty cell, or boards with the maximum number of empty cells, which is 81. Handling these scenarios correctly ensures the robustness of the solution. To solve the Sudoku solver problem, we first need to understand the constraints. A valid solution ensures that each row, column, and 3x3 subbox contains all digits from 1 to 9 exactly once. This makes the problem a classic example of a constraint satisfaction problem. Several approaches can be considered to tackle this. The brute force approach, for instance, involves generating all possible combinations of numbers for the empty cells and checking if they satisfy the Sudoku rules. While this is straightforward in concept, its time complexity is exponential, as it examines an enormous number of configurations. This makes it computationally impractical for anything but the simplest cases. A more refined approach is optimized backtracking with constraint checking. Here, instead of blindly generating combinations, we selectively place numbers in empty cells only if they adhere to the constraints. Backtracking allows us to undo decisions and explore alternate solutions when we hit a dead end. This method is more efficient than brute force, as it avoids invalid configurations early on, saving computational time and effort. Optimized backtracking builds on key observations to improve efficiency. First, the Sudoku constraints, ensuring unique numbers in rows, columns, and subboxes, can be checked in constant time by using hash sets to track used numbers. This allows us to quickly verify whether a number placement is valid. Additionally, by pruning invalid configurations early, we significantly reduce the search space. The time complexity for this approach is 9 to the power of m, where m represents the number of empty cells. While still exponential, this is a dramatic improvement over brute force, which examines every possible board configuration. However, optimized backtracking alone may not always be the most efficient. Constraint propagation, an advanced technique, can further reduce the search space. By applying heuristics like the minimum remaining value, we prioritize filling cells with fewer valid options first, which often leads to faster solutions. This involves tracking the possible values for each empty cell and updating neighboring cells' constraints after each placement. While this approach can handle complex edge cases more effectively, it introduces additional pre-processing overhead and complexity, making it challenging to implement. For this problem, the strategy we chose is optimized backtracking with constraint checking. This method strikes an ideal balance between simplicity and efficiency, making it a perfect fit for solving a standard 9x9 Sudoku puzzle. By leveraging the puzzle's constraints to prune the search space, we avoid the inefficiencies of brute force. While constraint propagation could offer further optimization, the added complexity is unnecessary for a problem of this scale. Optimized backtracking is efficient because it significantly reduces the number of recursive calls compared to brute force. It is also straightforward to implement and debug, which is an important consideration when working with algorithms. This approach is well suited to handle typical 9x9 Sudoku grids without excessive pre-processing. Of course, there are trade-offs. While constraint propagation might provide better performance for larger boards or more complex scenarios, it is overkill for this problem. On the other hand, brute force, though simple, is computationally infeasible. In summary, the chosen strategy of optimized backtracking with constraint checking offers a practical, effective, and balanced solution to the Sudoku solver problem. To solve the Sudoku board, we rely on a backtracking algorithm, which is a depth-first search strategy. This method involves incrementally placing digits while ensuring that constraints are not violated, and backtracking if we encounter a dead end. The first step is to identify an empty cell on the board. These empty cells are represented as dots. If no empty cells are left, the board is solved, and we terminate the recursion. Once an empty cell is found, we then attempt to place digits from 1 to 9. Before placing any digit, we validate it against Sudoku's constraints. The digit must not already exist in the current row, column, or the 3x3 subbox that the cell belongs to. If the digit passes all these checks, we place it in the cell and proceed recursively with this placement. If the recursive call is successful, it means the board is solvable with the current placement, and we can return true. However, if the recursive call fails, this indicates that no valid configuration is possible with the current digit in that position. In such cases, we backtrack by removing the digit and trying the next possible digit. If none of the digits from 1 to 9 satisfy the constraints for that cell, we return false, signaling that the board is unsolvable with the current configuration. The base case for this recursion occurs when all cells are filled, and the board satisfies all Sudoku constraints. This signals success. Once the board is solved, the recursion unwinds, and the solution is reflected in the board. Backtracking is effective because it systematically explores all configurations while pruning invalid paths early, saving time and computational effort. The recursion depth depends on the number of empty cells, and in the worst case, this means at most 81 recursive calls for a 9x9 board. The efficiency of backtracking is heavily reliant on constraint validation. By checking rows, columns, and subboxes for validity, we ensure that only feasible placements are explored. Pruning plays a crucial role here. Invalid placements are immediately rejected, significantly reducing the search space. To implement this, we use the input board, which is represented as a 9x9 grid. Each element in this grid is either a digit from 1 to 9 or a dot, which signifies an empty cell. For instance, a partially filled board might look like a two-dimensional list in Python, where empty spaces are denoted with dots. To validate constraints, we can use loops to check rows, columns, and subboxes manually. Alternatively, we can use 3 separate sets to track digits already used in rows, columns, and subboxes, ensuring that each new entry is validated in constant time. Using sets for constraint validation allows us to track digits efficiently and perform lookups in constant time. Specifically, we maintain a set for each row to track digits used in that row, another set for each column to track column-specific digits, and a third set for each 3x3 subbox. This structure simplifies and accelerates the validation process. Key operations in the algorithm include finding the next empty cell, which involves scanning the board in O, n squared, time, and validating constraints for potential digits, which takes O, n, for each placement. The recursive backtracking process involves exploring potential placements and undoing them when necessary. In the worst case, the time complexity is O, 9 to the power of m, where m is the number of empty cells. Edge cases also need to be considered. For instance, if the board is already solved, the algorithm recognizes this immediately and terminates. If the board is unsolvable, all possibilities are explored, and the algorithm will correctly return false. Additionally, it's worth noting that the algorithm stops as soon as it finds one valid solution, even if multiple solutions are possible. Optimizations can greatly improve the efficiency of the algorithm. Pre-computing constraints for rows, columns, and subboxes allows us to validate placements in constant time. Early termination is another crucial optimization. Once a solution is found, there's no need to continue exploring further possibilities. Efficient traversal of the board can also reduce branching. For example, using a priority queue to prioritize cells with the fewest valid candidates minimizes the number of recursive calls needed, as the problem space narrows quickly. These optimizations ensure that the algorithm not only solves the puzzle but does so in a computationally efficient manner, even for more complex boards. Here, we begin by defining the solve Sudoku method within a class called solution. Inside this method, we first declare a helper function named is_valid. This function checks whether placing a specific number in a given cell is valid according to Sudoku rules. It starts by verifying the row, iterating through all cells in the row to see if the number already exists. Next, it checks the column by iterating through all rows in the same column to ensure the number isn't duplicated. Finally, the function validates the 3x3 subgrid. To do this, it calculates the starting row and column of the box using integer division and iterates over all cells in that subgrid. If the number is found in any of these checks, the function returns false. If none of these constraints are violated, it returns true, confirming that the number can be placed in the cell. This helper function is critical for ensuring that our Sudoku solution respects the rules of the puzzle. Next, we define the backtrack function, which is responsible for solving the puzzle using recursion and backtracking. It starts by iterating through each cell in the grid using nested loops. If it encounters an empty cell, represented by a dot, it tries placing numbers from 1 to 9. For each number, it converts it to a string and checks its validity using the is_valid function. If the number is valid, it temporarily places it in the cell and recursively calls backtrack. If the recursive call successfully completes, the function returns true, indicating that the solution is valid. However, if no solution is found, it resets the cell back to a dot and continues testing the next number. If no valid numbers can be placed in the cell, the function returns false, signaling the need to backtrack further. Finally, if all cells are filled correctly, the backtrack function returns true, and the solve Sudoku method is complete. This approach ensures that the solver explores all possibilities while adhering to Sudoku rules. Here, we start with the solve Sudoku method, which takes the Sudoku board as input and serves as the entry point for solving the puzzle. The method calls the backtrack function, which is our recursive helper to fill in the board. Inside backtrack, we iterate through each cell in the 9x9 grid. If we encounter an empty cell, represented by a dot, we attempt to place numbers from 1 to 9. For each number, we check if it's valid to place it in the current cell by using an external isValid method. If the number is valid, we temporarily place it on the board and proceed with the recursive call. If the recursion returns true, it means the board is solvable with this placement, so we return true as well. However, if placing the number doesn't lead to a solution, we backtrack by resetting the cell to its empty state and continue trying other numbers. If no number from 1 to 9 works, we return false, indicating that this path didn't lead to a solution. Finally, if all cells are filled without issues, the function returns true, signaling success. The isValid method is crucial for ensuring that our solution respects Sudoku's rules. First, we check the row by iterating through all columns in the given row. If any cell already contains the number we're trying to place, it returns false. Next, we verify the column by iterating through all rows in the given column. Again, if the number is found in any of these cells, it's invalid. Lastly, we check the 3x3 subgrid that the current cell belongs to. We calculate the starting indices of the subgrid using integer division and iterate through all cells within this subgrid. If the number is found anywhere in the subgrid, we return false. If none of these checks fail, the method concludes that placing the number is valid and returns true. With the closing bracket, we end the isValid method and the solution class. These two methods, backtrack and isValid, work together to explore all possible solutions for the Sudoku puzzle. By using recursion and backtracking, the algorithm systematically tries every valid configuration until the board is solved, ensuring that all constraints of Sudoku are respected. Here, we begin solving a simple Sudoku puzzle. The given board has some cells pre-filled, and others are empty, represented by dots. Our approach starts by identifying the first empty cell, which is located at row 0, column 2. To determine the correct number for the cell, we try each number from 1 to 9, checking if it adheres to the Sudoku rules. It must not already exist in the same row, column, or 3x3 subgrid. Testing the number 1, we find that it's valid. So, we place 1 in this cell, resulting in an updated board state where this previously empty cell is now filled with 1. This step lays the groundwork for solving the rest of the puzzle systematically. Now, we move on to the next empty cell, which is at row 0, column 3. Again, we test numbers 1 through 9. Numbers 1 and 2 are invalid due to conflicts with the Sudoku rules, but the number 4 is valid. So, we place 4 in this cell. The process continues recursively, addressing each empty cell in turn. If a number cannot be placed in the current cell after testing all possibilities, the algorithm uses backtracking. This means it reverts the last placement, revisits the previous cell, and tries the next valid number. By following this method, the puzzle progresses towards a solution. Eventually, all cells are filled, and we achieve the final solved board shown here. With this completed example, we've demonstrated the power of recursive backtracking in solving a Sudoku puzzle. Let's look at a more challenging puzzle. The input board here has fewer pre-filled numbers, making it harder to solve. Starting at row 0, column 0, we test numbers 1 through 9. The number 1 is valid, so we place it in this cell. Moving to row 0, column 1, we find that the number 2 is valid and place it there. The algorithm continues to fill cells in this manner, but sometimes it encounters situations where no valid number can be placed in a cell after trying all options. For example, at row 0, column 4, no valid number fits. This triggers backtracking, where the algorithm reverts to the previous cell, row 0, column 3, and tries the next possible number. This process ensures that the algorithm explores all potential solutions systematically, eventually leading to a completed board. The application of backtracking in this harder scenario highlights its effectiveness in solving even the most complex puzzles. To summarize, there are a few key observations about this solution. First, the algorithm relies on recursive backtracking to explore all possible placements for each empty cell while adhering to Sudoku rules. Second, the validation step is crucial. Before placing a number, the is_valid function ensures that the number does not violate constraints for the row, column, or 3x3 subgrid. Finally, the backtracking mechanism allows the algorithm to recover from dead ends by undoing placements and trying alternative numbers. This method guarantees that if a solution exists, it will be found, as the algorithm exhaustively explores all valid configurations. Overall, this approach combines systematic exploration with efficient pruning to solve Sudoku puzzles effectively. To analyze the time complexity of solving Sudoku using backtracking, we start by examining the backtracking function itself. This function works by attempting to fill each empty cell on the board, and in the worst-case scenario, there are 81 empty cells on a standard 9x9 board. For each cell, the algorithm tries placing numbers from 1 to 9, which can result in up to 9 recursive calls for every cell. When we combine these observations, the total number of recursive calls in the worst case can be approximated as 9 to the power of m, where m represents the number of empty cells on the board. Next, we consider the is_valid function, which checks if a number placement is valid by verifying the current row, column, and 3x3 subgrid. Each of these checks takes 9 time since the board size is fixed, leading to a total validation cost of 27 for each placement. Since this is a constant for a fixed-sized board, we can treat it as 1. The key point about validation is that it is repeated for every recursive call, but its cost does not grow with the board size due to the fixed dimensions of the Sudoku grid. This gives us the overall time complexity of the algorithm. In the worst case, we have up to 9 to the power of m placements, and each placement involves a constant time validation process. Combining these, the overall time complexity is 9 to the power of m, where m is the number of empty cells. Moving to space complexity, we start with the recursive call stack. Since the backtracking algorithm relies on recursion, the maximum depth of the stack corresponds to the number of empty cells, m. This means the space required for the recursion stack is m. Additionally, the algorithm operates directly on the input board, which is a fixed 9x9 structure. This storage requirement is constant and does not depend on m, making it 1. Looking further into space complexity, the is_valid function does not require any additional storage because all its operations are performed directly on the board itself. With this in mind, the overall space complexity is dominated by the recursion stack, resulting in m, where m is the number of empty cells. Now let's distinguish between different cases. In the best case scenario, the board is nearly complete, meaning there are very few empty cells. Here, the recursion depth remains shallow, and the number of placements required is minimal, leading to a time complexity close to 9 to the power of m, with a small m and a space complexity of m. On the other hand, the worst case scenario arises when the board is completely empty, which means m equals 81. In this situation, the algorithm explores all possible placements, resulting in the maximum time complexity of 9 to the power of 81, and a space complexity of 81. When comparing this backtracking approach to a brute force method, the difference in efficiency becomes clear. A brute force solution would attempt every possible configuration of the entire board, which would result in an astronomical time complexity of 9 to the power of 81, for a 9x9 Sudoku. In contrast, backtracking significantly reduces the number of recursive calls by pruning invalid placements early. This optimization ensures that the algorithm is practical for solving Sudoku puzzles. To mathematically justify the big O notation, we note that backtracking explores only valid configurations. For a 9x9 Sudoku, the maximum branching factor is 9 since each cell can take one of 9 values, and the depth of recursion is limited to m, the number of empty cells. This leads to the time complexity of 9 to the power of m. The space complexity is dictated by the recursion stack, which grows in proportion to m, resulting in m. When solving Sudoku programmatically, there are several common pitfalls to watch out for. First, it's crucial to validate constraints correctly. Each digit placement must satisfy the rules for rows, columns, and subboxes. Overlooking these checks can result in invalid solutions that break the rules of Sudoku. Next, be cautious about how you implement backtracking. Inefficient designs with redundant checks or unnecessary loops can slow down your solution. Always aim to prune invalid paths as early as possible to maintain performance. Another frequent mistake is failing to revert the board state during backtracking. If you modify the board in place and don't undo changes, it can lead to incorrect configurations. Edge cases are another critical area. Boards that are nearly solved or have very few clues can behave unpredictably if not handled properly, potentially causing infinite recursion or incorrect results. Finally, be aware that not all Sudoku boards have a unique solution. Depending on the problem requirements, you might need to find just one solution or all possible solutions, so clarify this before you begin coding. Now, from an interview perspective, this problem is an excellent way to showcase your understanding of backtracking, a fundamental algorithm for combinatorial search problems. You should be ready to clearly explain the structure of your recursive function and how you enforce constraints at each step. Additionally, focus on pruning. Describe how validating constraints early allows you to reduce the search space and avoid unnecessary work. Interviewers may also ask about trade-offs, so be prepared to compare backtracking to other approaches, like constraint propagation, where data structures like sets or hash maps can help track valid placements. It's equally important to explain how you handle edge cases, such as sparse boards or nearly complete ones, and discuss their impact on performance. Related problems like n-queens or word search can also come up, as they share similar backtracking concepts. For example, LeetCode's n-queens problems involve placing queens on a chessboard without conflicts, while valid Sudoku focuses on checking board validity. These connections can help frame your approach in a broader context. Finally, let's consider alternative approaches and the trade-offs associated with each. The most common method is backtracking, where you recursively attempt to place numbers and backtrack if a constraint is violated. This approach is straightforward and effective but can become slow as the search space grows. Another option is constraint propagation, where you maintain a list of possible values for each cell and update these possibilities as numbers are placed. While this can speed up the solving process, it requires more memory and careful bookkeeping to ensure consistency. Brute force, on the other hand, involves trying all possible permutations of digits, but it's generally infeasible for larger boards due to its exponential complexity. Discussing these methods helps to demonstrate your understanding of the problem as a constraint satisfaction problem. Sudoku is a textbook example of how recursive backtracking works hand in hand with constraint validation. In an interview, it's essential to highlight how you optimize your implementation, especially in challenging scenarios like nearly solved boards or those with multiple solutions. Testing your solution against a variety of boards ensures robustness and shows that your approach is well-rounded. Thank you for watching this solution to LeetCode number 37, Sudoku Solver. We've explored how backtracking can effectively solve constraint-based problems like Sudoku. Remember, mastering algorithms like this takes practice, so keep challenging yourself. Subscribe for more tutorials, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!